Hey everyone, welcome back to my YouTube channel. For centuries, we've looked up at the night sky and mapped our cosmic neighborhood, believing we understood the fundamental architecture of our solar system. You know, the 8 planets, the asteroid belt, the distant Kuiper belt. We've sent probes to the gas giants, landed rovers on Mars, and even touched the sun. But what if everything we thought we knew about our own backyard was incomplete? What if, far beyond the familiar, lurking in the frigid dark abyss, there exists an unseen world? A massive, enigmatic planet whose very presence subtly orchestrates the dance of countless icy bodies. Imagine a world so vast, so powerful, that its gravitational shadow stretches billions of miles, yet it remains hidden, a cosmic phantom defying our best telescopes. This isn't science fiction. This is the tantalizing, deeply unsettling mystery of our outer solar system, a paradox that demands an answer. How can a world potentially 10 times the mass of Earth remain elusive, a ghost in the cosmic machine? The implications are staggering, challenging our fundamental understanding of how planets form and how our solar system came to be. It's a cosmic riddle that has captivated astronomers, turning our quiet corner of the galaxy into a vast, unfolding detective story. But to understand this cosmic mystery, we need to go back to where it all began, to the first whispers of an unseen world that ignited a scientific quest spanning decades. The story of this unseen world, often dubbed Planet Nine, isn't a sudden revelation but a slow, creeping realization born from peculiar observations. It began not with a direct sighting, but with the subtle, almost imperceptible nudges felt across billions of miles. For decades, astronomers have been meticulously charting the Kuiper belt, a vast ring of icy bodies beyond Neptune, a relic from the early solar system. It's a chaotic place, yet within this chaos, patterns began to emerge, patterns that defied explanation by the known gravitational forces of our sun and the 8 planets. The first hints were subtle, like faint ripples in a pond, but they grew stronger. Scientists noticed that some of the most distant Kuiper belt objects, or KBOs, particularly those with highly elongated orbits, seemed to be behaving strangely. Instead of orbiting randomly, they appeared to be clustered together, their aphelia, the farthest point in their orbit from the sun, all pointing in roughly the same direction. It was like watching a flock of birds all suddenly veering in unison, without any visible predator. This was a significant anomaly. The gravitational influence of the known planets should have scattered these objects more evenly. This clustering was a red flag, a whisper that something unseen was at play. One of the key figures in this unfolding drama is Mike Brown, a planetary astronomer at Caltech, often credited with the discovery of Eris, a dwarf planet whose discovery contributed to Pluto's reclassification. Brown, along with his colleague Konstantin Batygin, found themselves staring at data that simply didn't make sense. Imagine trying to solve a puzzle, but a crucial piece is missing, and without it, the whole picture is distorted. They were looking at the orbits of these distant KBOs, specifically a group of 6 objects, whose most distant points from the sun were all aligned in a similar direction, and their orbital planes were also tilted in a similar way. The odds of this happening by chance were astronomically small, something like 1 in 14,000. It was a statistical anomaly too significant to ignore. Batygin, a theoretical astrophysicist, initially approached the problem with skepticism, attempting to disprove the pattern. He tried every known perturbation, every gravitational influence, but nothing could account for the observed clustering. It was a frustrating, yet exhilarating period of scientific inquiry. He tried to model what the solar system would look like if this alignment was random, and their simulations consistently showed that it should not be happening. This wasn't just a few rogue rocks. It was a systemic deviation from expected behavior. The tension mounted as their initial findings were met with both excitement and healthy scientific skepticism. Other astronomers tried to replicate their results to find alternative explanations. Was it observational bias? Were they simply looking at a subset of KBOs that appeared to cluster? But as more data came in, and as more sophisticated analyses were performed, the clustering persisted. The evidence, though indirect, began to solidify. It was like hearing footsteps in an empty house. You don't see anyone, but the sound is undeniable, suggesting a presence. The scientific community found itself at a crossroads. Either our understanding of the Kuiper belt and its dynamics was fundamentally flawed, or there was indeed an unseen gravitational shepherd, a massive planet, shaping these distant orbits. This was the moment the hunt for Planet Nine truly began, moving from a statistical curiosity to a full-blown scientific quest. The initial observations, once dismissed as noise, were now understood as the gravitational echoes of a hidden world, a world whose story was only just beginning to unfold. The investigation deepened, transforming into a cosmic detective story where gravitational ripples were the only clues. Imagine you're in a completely dark room, and you can't see anything, but you can feel the subtle movements of objects around you, inferring their size and location based on how they push or pull. That's essentially what astronomers were doing. The clustering of those distant Kuiper belt objects wasn't the only piece of evidence. There was another, even stranger anomaly. Some KBOs were orbiting perpendicular to the plane of the solar system. Think of our solar system as a flat disk, with all the planets orbiting roughly on the same plane. Now imagine a few objects suddenly deciding to orbit like a spinning top, completely out of sync with everything else. This was a profound deviation, and Badigian and Brown realized that a massive, distant planet, orbiting at an extreme tilt, could actually explain both the clustering and these perpendicular orbits. This hypothetical Planet 9, they theorized, wouldn't just be hurting the KBOs into alignment. It would also be pushing some of them into these bizarre, high-inclination orbits. It was like a giant gravitational slingshot, flinging some objects far out of the solar system's main plane. The models suggested a planet roughly 5 to 10 times the mass of Earth, orbiting somewhere between 400 and 800 astronomical units from the Sun. To put that into perspective, Neptune, our outermost known planet, orbits at about 30 AU. This hypothetical world would be hundreds of times farther out, in the true cosmic wilderness. The scale of this distance is mind-boggling. If Earth were a pea, the Sun would be a basketball, and Neptune would be about a mile away. Planet 9 would be somewhere in the next county, but here's where it gets even weirder. Simulations also predicted that Planet 9 itself would have an eccentric, highly tilted orbit. This wasn't just about finding a planet. It was about understanding how such a massive world could end up in such an unusual configuration. One leading theory suggests that Planet 9 might have formed closer to the Sun, like the other gas giants, but was then ejected outwards during the early, chaotic period of planetary migration. Imagine a game of cosmic billiards, where the massive planets are constantly jostling for position, and sometimes one gets knocked out of the game entirely, sent hurtling into the void. This idea of an ejected planet fits with some models of solar system formation, where a fifth gas giant might have been common. The scientific community, initially cautious, began to take these predictions seriously. The evidence wasn't just anecdotal. It was statistical, consistent across multiple independent observations and theoretical models. This wasn't a fleeting anomaly. It was a persistent gravitational signature. Every new observation of a distant KBO that fit the predicted pattern only strengthened the case. It was like finding more and more pieces of a puzzle that, when put together, clearly depicted a missing image. But even with all this compelling indirect evidence, the biggest challenge remained: direct observation. Finding a world so far away, so dim, reflecting so little sunlight is like trying to spot a single, unlit matchstick in a vast, dark stadium from miles away. It requires extraordinary patience, powerful telescopes, and a bit of luck. The stakes were incredibly high. If Planet 9 truly existed, it would rewrite our textbooks on planetary formation, forcing us to rethink the very processes that built our solar system. The hunt was on, and the suspense was palpable. The modern quest for Planet 9 is a testament to human ingenuity and our insatiable drive to explore the unknown. It's a high-stakes game of hide-and-seek played across billions of miles, where cutting-edge technology is our only hope. Telescopes like the Subaru telescope in Hawaii, with its massive 8.2-meter primary mirror, and the upcoming Vera C. Rubin Observatory in Chile are at the forefront of this search. These aren't just bigger versions of backyard telescopes. They are highly sophisticated instruments capable of capturing faint light from the most distant corners of our solar system. The Rubin Observatory, in particular, is a game-changer. It will survey the entire observable sky every few nights, creating a dynamic map of the universe. Imagine a surveillance camera covering an entire city, constantly looking for anything that moves. This continuous scanning capability drastically increases the chances of spotting a slow-moving, distant object like Planet 9. The search involves sifting through petabytes of data, looking for the faintest pinprick of light that moves across the sky over several nights, indicating an object in orbit around our sun. This isn't just about looking for a bright dot. It's about detecting a change, a subtle shift against the backdrop of countless stars and galaxies. It's a painstaking process, often relying on advanced algorithms and artificial intelligence to identify potential candidates. Scientists aren't just randomly scanning. They are focusing their efforts on specific regions of the sky where theoretical models predict Planet 9 is most likely to be found. These models, constantly refined by new observations of distant KBOs, act like a cosmic treasure map, narrowing down the search area. But even with these powerful tools, the search is incredibly challenging. There are conflicting theories about Planet 9's exact size, composition, and orbital parameters. Some models suggest it could be a mini-Neptune, a rocky core surrounded by a thick envelope of hydrogen and helium, while others propose it could be a super-Earth, a much larger, denser version of our own planet. Each theoretical possibility presents a different observational signature, making the hunt even more complex. It's like looking for an unknown animal, not knowing if it's the size of a mouse or an elephant or what color its fur might be. The scientific battle isn't just about finding it, it's also about understanding what we're looking for. Recent discoveries continue to fuel the excitement and frustration. In 2021, astronomers identified a new distant KBO, provisionally named 2018 VG18, nicknamed Pharos, located about 120 AU from the Sun, making it one of the most distant objects ever observed in our solar system. Then came 2018 AG37, or Farfarout, pushing the record to an astonishing 132 AU. These discoveries, while not Planet 9 itself, provide more data points, more gravitational ripples that can be used to refine the models and narrow the search. Each new distant object acts as another witness in our cosmic detective story, offering tantalizing clues about the unseen gravitational forces at play. The tension builds with every new data point, every new analysis. Are we on the cusp of a breakthrough? Will the next image from a powerful telescope finally reveal the faint, elusive signature of this hidden world? The feeling is that we are closer than ever before, standing on the precipice of a discovery that could fundamentally alter our understanding of our own cosmic home. Imagine the moment when that faint, moving dot is finally confirmed. A new planet in our own solar system, revealed after decades of searching. It would be a moment of pure, unadulterated awe, a profound reminder of the vastness and mystery that still exists within our grasp. If Planet 9 is indeed discovered, the implications for humanity's understanding of our place in the universe would be profound. It would rewrite the textbooks on planetary formation. Current models suggest that planets form from the accretion of dust and gas in a protoplanetary disk around a young star. The presence of a massive planet in such a distant, eccentric orbit would challenge these models, suggesting either a more chaotic early solar system than previously imagined, or perhaps even a capture event from another star system, though the latter is less favored. It would force us to confront the idea that our solar system, which we have meticulously charted and explored, still holds fundamental secrets, massive worlds hidden in plain sight. This discovery would connect to bigger existential questions. If our solar system can harbor such a massive, unseen world, what other hidden giants might be lurking in the dark fringes of other star systems? It would deepen our appreciation for the sheer scale and complexity of the cosmos, reminding us that even in our immediate cosmic neighborhood, the unknown far outweighs the known. It would ignite new waves of scientific inquiry, prompting further exploration of the outer solar system, not just for Planet 9, but for other potential hidden worlds or exotic phenomena. Upcoming missions and observatories are poised to continue this monumental search. The Vera C. Rubin Observatory, as mentioned, will be instrumental